Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion, where we are talking about Einstein's theory of relativity. Today, I want to talk about the phenomenon of time dilation. You're going to see that this is closely related to what we talked about in my last lecture, that is, how events that are simultaneous to one set of observers may not be simultaneous to another set of observers who are in motion relative to the first set of observers. That is, once one accepts that the speed of light is a constant, then one needs to have a more flexible understanding of the notion of time. And that's precisely the issue that comes up in the phenomenon of time dilation that I'll be talking about today. I'll probably have to break this up into a couple of lectures. So let's get started. What do I mean by time dilation, and how do we understand this? So the topic is time dilation. And I want to approach this by means of examples. So let's first of all consider a spaceship with a clock. So consider a spaceship with a special clock. And this clock, it consists of a ball that bounces back and forth between two bumpers. This might seem like an absurd kind of clock, but you'll see where I'm going with this. So let's suppose we have this ship like this. And let's put a person in this spaceship. We'll call this person Luke. Okay? And on either side of this ship, there is a bumper, a very reflective, rubbery kind of bumper that a ball can bounce back and forth between. And since this is in outer space, there's no gravity, so the ball doesn't tend to fall down. It's simply, if you get it going, it's going to bounce back and forth between these bumpers. So it'll go up like this, it'll bounce back and come back and bounce back, and it will just keep on doing that. This is the clock that he has on the ship. And so the speed that the ball is moving up, we'll call that speed u, and the speed it has when moving back down is also a speed u. Okay? And if the width of the ship is given by d, that's the width of the ship, then we can determine how much time elapses between each bounce of this ball off of plate 1 on the bottom. Okay? So what happens is the ticks of this clock are associated with whenever the ball makes contact with the bottom plate. So they occur whenever the ball strikes against the bottom plate. Okay? So, according to Luke, who's measuring this, we could talk about the difference in time, delta t, as measured on Luke's clock. That's what the subscript L indicates. The time interval between bounces of this are going to be determined by how far the ball has to go and its speed. In particular, the distance it moves is going to be 2d, and the speed with which it moves is u. So this is just a case, if you can probably see, if you rearrange this, you get the speed of the ball is the distance it moves over the time, and here I've just solved for the time between ticks in terms of the distance and the speed. So there's nothing controversial up until this point. So this is the time interval between ticks of Luke's clock as measured by Luke. Okay, now here's where I want to go with this. Let's consider another person who is outside the ship watching the ship rush by at some high speed. So now I want you to consider John, an astronaut outside the ship. So outside Luke's ship. And he's watching Luke's ship fly by at some high speed, and we'll call that speed v. Okay? So of course, from Luke's perspective, he's sitting still in his ship, and John, who's outside, is flying past in this direction at speed v. But John, who's outside the ship, instead sees Luke's ship rushing by at speed v. So they agree on their relative speed, they just disagree about who is really at rest and who's really in motion. And that's going to be, as we might recall, one of the main themes in the theory of relativity. People agree about the relative speed of each other, they just disagree about who's at rest and who's in motion. And there's no principled way of saying who's really at rest and who's really in motion, because there's no absolute notion of space. Okay, so here is Luke in this ship, and once again, this ship, we imagine it to have glass walls so John can see what's going on inside of the ship. Okay, so I'm going to draw these bumpers. So here's the bumper on the bottom of the ship and on the top of the ship. And let's suppose at this particular instant the ball is making contact with the bottom bumper. Now, of course, the ship is moving at speed v according to John, who's outside here. And it doesn't have to be just a single astronaut. It could be a whole host of John, once again, and his friends who are all observing what's going on. The point is that they're all at rest relative to one another, and they're all watching Luke and his ship travel past. Okay, so this is kind of, if this is a cartoon where I'm capturing different frames at different moments in time, at this moment, the ball's making contact. A moment later, the ship will have gotten to right here. Okay, I'll draw Luke once again in here. Remember, this is Luke in the ship, and this is John outside watching. And I'll draw these bumpers once again. And this ball, as John sees it, is going to be following this trajectory. I'll maybe make this a blue trajectory. It's going up like this, and the ball is bouncing. Maybe I'll make the ball red to highlight it. So here's the ball, and then it bounces off of this plate, like this. Here's the ball. And then, a moment later, the ship will have gotten over to here, kind of drawing 3 subsequent moments in time. Okay, and now that ball will have followed this trajectory. Whoops, that's not a very straight line, but you get the point. And it goes like this. So we have these ticks. So here's the first tick of the clock when the ball hits right there, and then it hits this bumper, and then it comes down over here, and this is the second tick of the clock. Okay? So notice what's happening here is that John will see the ball undergoing a different trajectory than Luke. Luke saw it bouncing straight up and down and measuring the ticks as the ball is bouncing off the lower plate. John also sees the ball bouncing off the lower plate, but he sees the trajectory as following this kind of diagonal path up and this diagonal path down because he sees it in motion. Now, the question I want to ask is, how much time does it take for Luke's clock to tick according to John? I'll write that question down. So here's the question. How much time does it take for Luke's clock to tick according to John? So maybe John has a little clock that's right next to him, and he's measuring the ticks between his clock and comparing it to the ticks between on Luke's clock and seeing which one is ticking at a higher rate. If these were identical kinds of clocks, they should be ticking at the exact same rate. Okay, now one way to think about this is, well, John would have to measure the time interval between the ticks of Luke's clock according to John. So this would be the time interval between ticks of Luke's clock. That means the clock that is on Luke's spaceship. But this is as measured by John. That's what I mean by this J subscript. It's John is doing the measurement. In this case, sub L, that means Luke is doing the measurements. They're both measuring the ticks of the clock that's on Luke's ship, but the subscripts indicate who is doing the measuring. How do we figure out this? Well, once again, it has to be the distance the ball moves divided by its speed. What is the distance that this ball moves? Well, it's obvious from looking at this picture that the ball is moving a different distance according to John than according to Luke. So if I put a little S right here, that indicates the length of this diagonal line, and S right here, that's the length of this diagonal line. So the distance that it has to move is 2s. Instead of just 2d, it's moving 2s. What about the speed with which it moves? Well, the ball was flying upward at a speed u, but the ship is moving rightward at a speed v, and so you're going to have to compound these two velocities. You're going to have to somehow add the speed of the ship to the speed of the ball, and that's going to be a different speed. So we're going to put w right here. So this is the speed of the ball according to John, and this right here was the distance that the ball moves according to John. And that combination, the distance over the speed, should give you the time between ticks of Luke's clock as measured by John. Let me give you a heads up of where we're going with this, and then I'll probably take a break for a moment. What I'm going to point out here is that although the distance the ball moves is greater, according to John, the speed is also greater, and they're greater in the exact same proportion. So that means that you end up getting, I'm kind of giving it away here, you end up getting that the time of ticks as measured by John is going to end up being the same as the time between ticks as measured by Luke. This is kind of using a traditional analysis of this. We're going to find that that's the case. Okay, so maybe what I'll do is I'll take a break here and I'll show how this works out.